In this video, we'll be discussing magnetic properties of matter from HC Verma Objective 2. So, the first question is, we have to pick the correct options. All electrons have magnetic moment, yes. Any isolated charge which is moving should have a magnetic moment. So, all protons have a magnetic moment, yes, it is also correct. But it is not necessary for an atom or a nuclei to have magnetic moment because one charge may cancel the magnetic moment of another charge. Okay, so C and D are not the correct options. We are left with A and B. Again, the permanent magnetic moment of the atom of a material is not zero. So the material can be paramagnetic or a ferromagnetic. Okay, it can be para or ferro. It should not be diamagnetic. So the only correct option is D. Again, the only correct option is D because it is option A is saying that it must be paramagnetic. No, it must not be paramagnetic. It may be a para or a ferro. Hence, the only correct option we have is D. In the next question, the permanent magnetic moment of an atom in a material is zero. The material should be obviously diamagnetic. So, because the diamagnetic materials have zero permanent magnetic moment for individual atom in the absence of any external magnetic field, uh, the magnetic moment appear when the external magnetic field is applied. Okay, and in the next question, which of the following pairs has quantity of same dimensions: magnetic field and magnetizing intensity? H, B and H. No, they don't have same dimension because H is defined as B by mu naught. Again, magnetic field and I is also defined as B induced by mu naught, so they will not have same dimensions. Magnetizing field intensity H and magnetization intensity of magnetization. Obviously, these two have same dimension. This is B external by mu naught and this is B induced by mu naught. Dimensionally both are same. Longitudinal strain, it is a dimensionless quantity, and magnetic susceptibility is also a dimensionless quantity. It is the ratio of I and H. So obviously both are dimensionless, so they are same in dimensions. So C and D are the correct options. When a ferromagnetic material goes through a hysteresis loop, the magnetic susceptibility. Okay, let's have a look at the hysteresis loop. We can say this is the hysteresis loop. Okay, let me find the cursor. Okay, this is the hysteresis loop, and at this point, we can say at this point, point number one, I is something and H is 0, so the ratio will tend to infinity, and somewhere in between I is positive, H is negative. So in the second quadrant we can say the ratio is negative, and at point 2 I is 0 and H is something, so Xi will be 0. And the in the fourth quadrant also Xi will be negative. So we can say it will be 0, it will be negative, it will be infinite, it may be positive also. So it will not be constant as it is defined as the ratio of I versus X. Okay, so the correct options are B, C and D. Mark out the correct option. Diamagnetism occur in all material. Yes, it is because of the external magnetic field and orbital motion of electrons. So it occurs in all material. Diamagnetism result from partial alignment of no, there's no alignment in diamagnetism. So B option is wrong. The magnetizing field intensity H is always 0 in free space. Okay. Option C is wrong because there can be external magnetic field in space. Magnetic field can exist in free space or in vacuum. So H can be there even in vacuum. The last option is the magnetic field of induced magnetic moment is opposite to the applied magnetic field. Obviously, the magnetic field due to induced magnetic moment will be opposite to the applied magnetic field. So the only correct options are A and D. Thank you.